So far we have understood the background of our problem, that what all equations we are going to use in the problem and how they are derived. Now let us understand the conditions which we will be using in our problems. Let us understand our problem in detail. What are the conditions, what are the velocities we will be using in our problems, what is an incompressible liquid, and how the laminar state is affecting our problem, how the two regions are divided in our problem. So let us understand all of this. So now let us understand our problem statement, and let me first read the statement. Here it is given that the fluid is placed in between two cup arrangement as shown in the figure. So you can see that the arrangement is given. This is the outer cylinder, the dark shaded one, and there is an inner cylinder which is being shaded light. And the fluid is placed between the region of these two cylinders. Then the outer curve is made to rotate with a constant angular velocity omega naught, that is in radian per unit time. So here it is given that the outer cylinder is connected to a shaft which is being rotated at the angular speed of omega naught, and the fluid will also rotate with the same angular speed. The conditions of measurement are controlled so that there is steady flow. It is given in the problem. The problem is at steady state. We will understand each and every term in detail further. The tangential and laminar flow is in the annular region. It is also given that there is laminar flow in the region. Uh, because of the arrangement used, all end effects are negligible. It is also given that the end effects are negligible. So we will understand what are end effects, and we will go into its detail. So here we have to derive its velocity profile, assuming the fluid is Newtonian and it is of constant viscosity and density. So this is a problem statement and the setup which is given, and let us dive deep into the details of this problem. Here you can see in the diagram, as it is given that the radius of the outer cylinder is r and radius of the inner cylinder is k times r. So the fluid is placed between the region of this k times r, and it is being rotated at this speed. So now as we have read the problem, we can see that this problem describes a classic fluid mechanics scenario known as the coed flow of coaxial cylinder system. This type of flow occurs between two infinitely long coaxial cylinders where one cylinder is stationary and the other rotates with an angular velocity. uh, we need to find its velocity profile and flux profile. So let us list out the assumption which will be necessary for this problem. So to derive the velocity profile equation, we have made several assumptions. Let us list them down. Firstly, the flow is steady state. That is given in the problem. So for this, the explanation is the system is assumed to be at steady state, that is the velocity does not change with time. So del v theta by dt is 0, that is v theta velocity is not changing with time. The outer cylinder rotates at an angular velocity sigma naught, and the inner cylinder is stationary. Since there are no transient forces or time dependent inputs, the flow remains unchanged over the time. In real world application, if the outer cylinder suddenly starts rotating, the flow would initially be unsteady. However, after short time, the system reaches an equilibrium steady state and velocity stops changing with time. So we are assuming that the system has already reached its steady state. So we have started the problem when it has already been reached on the steady state. Secondly, the flow is asymmetric, axis symmetric. That is, it is symmetric around the theta. So velocity theta is not changing in the theta direction. That is, del v theta by d theta is equals to 0. So that is, there is no dependence on angular velocity coordinate theta because the system is cylindrically asymmetric. Cylindrically symmetric. The fluid velocity at a given radius r is same at all angles around the cylinder. Physical meaning is, since the problem involves a rotating outer cylinder and stationary inner cylinder, no preferred direction exists in theta, meaning velocity changes only in r direction. So we know that the velocity is only changing in r direction and it's not changing in theta direction. The assumption is valid as long as there are no external disturbances. Example like rough surfaces, external forces acting in theta direction. Third assumption is the flow is fully developed. That is, del v theta by del z is equals to 0. That is, v theta is not changing in the theta z direction. Explanation is, the system is assumed to be infinitely long in the axial direction, meaning flow properties do not change along the z. That is, the coaxial cylinders have an infinite length, so the properties are not changing in z direction. Velocity only varies in r direction. Physical meaning is, if the cylinders are very long, then far from the ends, fluid elements experience the same forces everywhere along there. That is, the forces experienced in the z direction are same everywhere in the fluid. The assumption is used in practical problems where end effects, that is entrance and exit effects of finite cylinders, are negligible. So here the end effects are negligible, so that the v theta is not changing in z direction. Fourth assumption is the fluid is Newtonian. That is, fluid is assumed to be Newtonian of constant viscosity. So we can apply the Newton's law of viscosity in the problem. That is, tau, that is moment of flux, is equals to mu dv by dy. That is velocity of y differentiated with respect to y, where tau is the shear stress directly proportional to the velocity gradient. This means that fluid has a constant viscosity, that is, fluid is Newtonian. Physical meaning, the most common fluids, water, air, oil, at lower shear stresses behave as Newtonian fluid. However, non-Newtonian fluids, example blood, polymer solution, exhibits viscosity change under shear and would require a different analysis. So the polymer solution or blood, these solutions can change viscosity. So they would there we cannot use the Newton's law of viscosity. There we need to do a different approach. Fifth assumption is there is no radial and axial velocity. That is, the velocity in r direction and velocity in z directions are zero. The explanation for this, the fluid moves purely in tangential theta direction. That is, the flow is only in theta direction. So this is given in the problem. There is no radial flow component, that is Vr, because the wall prevents movement towards or away from the center. And there is no axial flow component, that is Vz, because the problem is radially confined and assumed infinitely long. So this is the explanation for that. The physical meaning, if there were pressure gradient in the radial or axial direction, the additional velocity component Vr or Vz would arise. But here we have assumed that the pressure throughout the liquid is constant, as it is an infinitely long cylinder, properties are not changing. So Vr and Vz are 0. However, in this problem, the flow is purely rotational and driven only by the motion of outer cylinder, making the assumption valid. That is, we are not considering the effect of gravity. Sixth assumption is negligible pressure gradient. That is, del p by del theta is equals to 0. We are assuming that pressure is not changing in theta direction. There is no external forces tangential direction except for the shear force from the rotating outer cylinder. So there is only the drag force of, through the walls of rotating outer cylinder. If there were a pressure gradient in theta direction, it would introduce additional tangential forces, but in our case it is not like that. Physical meaning: in coiled flow between moving plates or cylinder driven by shear, motion is not pressure driven, it is only by the drag or the moving boundary of the cylinder. Here it is, in our case it's outer cylinder. The assumption holds as long as the fluid is not subjected to external tangential forces. So here we are not taking any tangential forces, our system is at steady state. Seventh is no slip boundary conditions. So we are considering that there is no slip between the fluid and the last layer of fluid and the layer of the wall, that they are being rotated at the same velocity, so there is no slip condition. Solid Here it is written that the no slip condition states that the fluid in contact with a solid surface has zero relative velocity with respect to the surface, that is the same meaning. At the inner stationary cylinder, r is equals to kr, the tangential velocity is 0. That is v theta at kr is equals to 0 or kappa r. At the outer cylinder, r is equals to capital R. The tangential velocity matches as the velocity of the cylindrical wall, that is omega naught r. So this is the velocity of the outer cylinder, and the fluid last layer also moves with the same velocity, so there is no slip between them. The assumption is experimentally valid for viscous forces, that viscous fluids that we are using, that is like water and oil, all those are fluids are incompressible. At the molecular level, fluid molecules stick to the solid surfaces, creating a boundary layer that enforces this condition. Our eighth assumption is the flow is laminar. So here explanation is the analysis assume that the flow is laminar, meaning fluid layers move smoothly without chaotic mixing. That this is only a one-dimensional flow, and it is a laminar flow. There are no turbulences, and Reynolds number is given by rho v theta r by mu, and Reynolds numbers remains in the laminar region, that is less than 2000 in cylindrical geometry. If the outer cylinder rotates too fast, the flow may become turbulent, introducing additional fluctuations. But here it is in the question it is stated that the cylinder is moving at a slow speed. The assumption is valid when rotation speed is moderate and the fluid viscosity is high enough to damp turbulence. So it is valid when the speed is moderate. So we have assumed that it is a slow speed. So in our case, the flow is laminar, and all these assumptions are valid.
So from the assumptions, we state that first v theta is equals to Vr. As v theta is the only function of Vr, this is due to the 1D laminar flow, and as the velocity is symmetric within the theta direction, so velocities in z direction are 0. So that's why v theta is only the function of Vr. Again, Vr and Vz are 0. This is because the negligible end effects. And to derive the velocity profile, we are only interested in theta component. So to derive the velocity profile, we are only interested in theta component. This is because the velocities in r and z directions are 0. So now we will see in the Navier-Stokes equation using the cylindrical coordinates that we'll use the theta component to derive the equations. Let's write the theta component as so the equation of theta component we can write as rho dv theta by del v theta by del t plus vr del v theta by del r plus v theta upon r into del v theta by del theta plus vz into del v theta by del z plus vr v theta upon r, so which is equal to minus 1 by r del p by del theta plus mu square bracket del by del r into 1 by r into del by del r v theta plus 1 by r square del square v theta by del theta square plus del square v theta by del z square plus 2 by r square del vr by del theta square bracket closed plus rho g theta. So now you can see here we have written the Navier-Stokes equation for the theta component. So one by one we'll try to understand how we will use this equation and how these terms will be get cancelled and what will the output of this equation. So as we see here, the first term del v theta by del t is equals to 0. This is because steady state flow, so we'll cancel this term. Secondly, Vr del v theta by del r is again 0. This is because we are giving it that Vr is 0, so that's why the whole term will be cancelled. Next, v theta by r del v theta by del theta. So this is 0 because v theta is only a function of r. So when we differentiate this with respect to theta, it will be 0. So again, this term will be 0. Now we can see here Vz into del v theta by del z is again 0. This is because the value of Vz is 0 as we have stated in assumptions. So we again cancel this term. This will be equals to 0. Again similarly Vr into v theta by r is equals to 0. This is because Vr is 0. So again this term will be 0. Now let's come to the right hand side. So minus 1 by r del p by del theta is equals to 0. This is because the p here is constant. So minus 1 by r del p by del theta is equal to 0. Again we'll cancel this term. So now this term is a non-zero because it's not satisfying any of these assumptions above. We'll move on the next term. 1 by r square into del square v theta by del theta square. This is 0 because again the same reason that v theta is a function of r, and if we differentiate this with respect to theta, it will give 0. Again this term will 0. Next, del square v theta by del z square. It's again 0. The same reason, v theta is only the function of r. So again we'll get this as 0. So again the next term 2 by r square del Vr by del theta is again 0 term. This is because Vr is 0 here. And now coming to the last piece, we have rho g theta. This is 0 because there are no external forces and the flow is purely rotation. So we consider this as 0. So by reducing here, we are only left with this term. And similarly, we can also perform it for the r component. So we have written here the r component equation, Navier-Stokes equation. So similarly, we can also see here that this first term is also 0 because Vr is 0. So this turns out to be 0. Second term is also 0. This is because Vr is 0. It is also turns to 0. And third term, v theta by r del Vr by del theta is again 0 because Vr is again 0. And the fourth term, Vz del Vr by del z is again 0 because Vz is 0. Now the next term, this term is a non-zero because v theta is a function of r, and this is not 0. And the next, this term is not 0 because pressure is changing in r direction. So the value of this differential will be a non-zero value. Coming to the next, these values will also be 0 because Vr is 0. This term will also be 0 because Vr is 0. And this term will also be 0 because v theta is in function of r, so the differential will be 0, and this will also be 0 because purely rotational flow. So by writing this, we are only left with the terms as minus rho v theta square by r is equals to minus del p by del r. And again, similarly, we can also write this for the z component. So for z component, so let us see in z component, we see here that again this term is also 0 because vz is 0. This term also becomes 0 because vr is 0. Similarly, this terms also become 0 because vz is 0, and again this term will also be 0 because vz is 0. This term is a non-zero because pressure is changing in z direction also, so this is a non-zero value. And again this term also becomes 0 because vz is 0. Similarly, this also becomes 0 as vz is 0. Same reason for this also, as vz is 0, and this will be a non-zero term because uh, the gravity is acting in the z direction. So writing this, we get as minus del p by del z plus rho g z is equals to 0. We'll give this as equation 3.
So now let us see the boundary conditions for a region. So considering the region 1, we can see that our first boundary condition can be at r is equals to kappa r, that is at the wall of the inner cylinder, the velocity, that is the v theta component, is 0 as our inner cylinder is stationary. So here there will be no velocity of the fluid, the velocity of fluid here will be 0. And the second boundary condition we can consider as at r is equals to capital R, that is at the wall of outer cylinder, the velocity v theta component will be maximum and will be equal to the velocity of the outer cylinder, that is omega naught r. So we have written the boundary condition at r equals to kappa r v theta is equals to 0, and at r equals to capital R, that is at outer cylinder, v theta is equals to the angular velocity of the outer cylinder, that is omega naught, into the moment arm, that is r. So let us derive the velocity profile for the region 1. We can see that the theta component we are left with is d by dr is equals to 1 upon r d by dr of r v theta is equals to 0. So let us integrate this equation. On integrating, we will get d by dr of r v theta is equals to c1. This is the first equation we will get. And on further integration, again we can see that r v theta is equals to c1r dr, that is r v theta is c1 r square by 2 plus c2, that is v theta is equals to c1 r by 2 plus c2 by r. This is our velocity profile equation with the unknown constants. Now we have to find the value of c1 and c2 for these equations. So we will be using the boundary conditions. So we will be putting our boundary condition in the equation. So at r is equals to kappa r, v theta is equals to 0. So we will get c1 kappa r by 2 plus c2 upon kappa r is equals to 0. So this equation we can give small a. Putting second boundary condition, that is at r is equals to capital R, v theta is equals to omega naught of r. So we will get omega naught of r is equals to c1 capital R by 2 plus c2 by r. Now we have to solve these equation A and B simultaneously to get c1 and c2. On solving, we get the values of c1 and c2. So we can subtract firstly uh, this equation B by equation A, and by taking 1 upon kappa from the equation A common. So we will get, so on solving we will get the constant set c1 is equals to minus 2 omega naught upon k kappa into kappa minus 1 upon kappa, and c2 is 2 into omega naught kappa r square upon kappa minus 1 upon kappa. So by putting the values of c1 and c2, we will get this final velocity profile equation for the region 1 as v theta is equals to omega naught r into small r by kappa capital R minus kappa capital R by small r upon 1 upon kappa minus kappa. So this will be the final velocity profile equation, and through this we will draw our velocity profile that we will see further. Now for the region 2, similarly we will do the derivation. We will be deriving, we will be putting the boundary condition and deriving the constants, and we will get the velocity profile equation. We can similarly consider a case 2 also, where we can consider that the outer cylinder is, we can similarly consider a case 2 also, in which we are considering that the outer cylinder is stationary and our inner cylinder is rotating as a speed of omega I. So here we will get the boundary condition as at r is equals to kappa r, v theta will be equals to omega I kappa r. That is at the wall of the inner cylinder. It will be the velocity of fluid will be equals to the velocity of inner cylinder, and at r is equals to capital R, that is at the wall of outer cylinder, will be 0 because in our case the outer cylinder is held stationary. So by putting these boundary condition, we will get the velocity profile as v theta is equals to sigma I kappa r by r minus r upon capital R whole upon 1 upon kappa minus kappa. So this is the velocity profile for case 2. But in our problem we have considered case 1, in which the outer cylinder is moving and the inner cylinder is at constant is held stationary. So we will only consider the velocity profile, and we will see how this velocity profile is drawn and how it varies in the region.